Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, we'll just check whether we're actually on starting time. I think we are. Yes, 2:05. Okay. Come back to that in a second. So this is where we left the stuff yesterday, so following on from that workshop. And I'm going to try and fill in the other two bits on the back of the page for the workshop, to answer try and answer the research question using this analysis. Now remember, we did have a problem with the things here. We've got two outliers in one of the groups. It's inflating the variance for that group. I think later on in the code I do a check for, there's a rough rule of thumb that if the variance of the largest group to the variance of the smallest group is more than the number of groups, it's probably a problem. Okay? That rule of thumb's in the brick somewhere, and like most rule of thumbs, I ignore it when it's not really convenient. Would I worry about this situation? Well, there's a real downside to deleting observations from a balanced design. You unbalance the design. It makes the maths and all the other stuff a bit more complicated. So you're highly reluctant to do it in an experimental design situation. You probably would do it if you got back to the people who did the experiment and you found that, yeah, okay, the reason we had a real problem there is because there were certain incidents that happened and these just aren't valid observations, in which case you probably would remove them and treat this as an unbalanced design. In this situation, what's happened though is it could be that really the mean for this group's been artificially inflated. In fact, these two are the outliers, and this is where the majority of that group is. Or it could be that these two are the outliers, and that's where the majority of the group is. But really, what we've got is we've got a more variable group. What's that going to do overall? Having one group more variable than it should be. So actually what it's going to do is actually not too harmful. It's going to inflate this. Okay? It's going to inflate the error variance.
Wouldn't it mess up the whole comparison, but since it's the control variable, the one that's getting...
Well, it's arguably messing up all three comparisons, all three of the main comparisons we're going to make here. But in what way does it mess it up? Now, if the error mean square gets larger, actually all the standard errors are based on that because that is our estimate of sigma squared in any linear model. So what we've got is that we've got an overestimate for sigma squared. That means all our standard errors are too large. If we start conducting t-tests, they're actually less likely to be significant than they would otherwise be. What it's likely to do is to err our inference on the conservative side. Now, if I'm happy with that, I mean, if I'm happy to sort of say, look, if it's on the conservative side and it still seems to be significant, then I'm actually not too unhappy. Okay? So in this situation, I probably wouldn't make a correction. We will talk a little bit more about outliers later on as we get further into the course. But in this one, I think it's possibly ignorable. Okay? I would always ignore these sorts of problems. It's a matter of judgment. Because I can't go back to the original experimenters in this one, because like I said in the workshop, I don't know who the people who really collected this. I haven't even found the original reference for this one. Steve Stern obviously found it from somewhere in the 1990s. I presume he found it in one of the old classic Rothamsted textbooks. Well, the data is probably back from about the 1930s, yes. Okay. So let's ignore that for the moment and see how we do inference with these things here. Notice we've already sort of seen what happens when you do dummy variable coding. That's the intercept. That's the difference between that particular fertilizer treatment and the intercept group. Okay? And that's the difference between that fertilizer treatment and the intercept group. And the intercept group we worked out was the control group, okay, because of the way they were coded. So, what is this F-test telling us, first of all? Not all treatment means the same. Okay? Now, I'll come back to this later on today, but Fisher's approach would be to sort of use that as a first filter test, done at the right level of comparison. He would decide in his alpha a priori, and then sort of say, look, if that's less than my alpha, then I expect to find some differences between the groups. So he'd use that as a filter before he went any further. Notice we're now making 3 comparisons to test each of the fertilizer treatments against the control group. What's the problem with making multiple comparisons? If I make 3 comparisons at the 95% confidence level, do I have overall 95% confidence? No. That's the problem. It's the problem with multiple comparisons. That we'll also come back to later today. But, okay, we've gone through the first test and we're told that not all the means are equal. What do these ones tell us? Well, it tells us that this one is significantly above. Even with inflated variances, the best treatment seems to be significantly above the overall average. And really, if what we're looking for is the thing that gives us the maximum yield, we've basically answered the research question, haven't we? The best fertilizer treatment for the maximum yield is going to be the one that gives us the most significantly above the mean, above the control group, this one here. It's not fully answered it. There's one other comparison we probably should make. And it's not made on this table. What's the other what are the other thing we could be interested in here? Let's say it was a bit cheaper to treat with this fertilizer treatment than it was to treat with that fertilizer treatment. Okay, both of them are giving improvements, arguably. Though this one's arguably not significantly better with the inflated variance than the control group. But we would probably be interested in whether that's significantly better than that. Do we really have to go to the extra expense of the best fertilizer treatment? Okay, so that's probably how you'd work through this. Now notice I've done it in such a way as I made the minimum number of comparisons. I'd used one filter test, then I basically picked out this one as being the most comparison of most interest, and then I thought, well, there's also an interest in comparison there, which I'll have to do some more calculations to actually make. Okay, so what I have to grind through now is a little bit of the theory about what we're actually doing in the background here, what I was doing in the background here, and that's this stuff I was starting on the document camera. So, treatment, contrasts, or coding, which is what we've used here, involves a series of dummy variables, k minus one of them. The kth dummy variable is not needed or is superfluous. I think it's spelled superfluous. It would be equal to 1 when all the others are 0. So if we actually included k dummy variables for a k-level category variable, what's going to be the problem that happens in a multiple regression model? I can predict the value of the kth one from the previous k minus 1. Perfect multicollinearity. Good. So in other words, what we describe a model, if you fitted that model, as being over-parameterized. Okay, we'd have one more parameter than it really needed. The category choose And we can choose this to not have its own indicator, is the reference category. In treatment coding, the obvious thing to say is the reference category. In treatment coding, we'd set up it as the control group or the no treatment group. Okay, that's not the only situation we might want to do, though. We might want to, instead of comparing things to some sort of control group or reference group, we may want to compare things, well, I mean, think about the male-female business. There's no necessary reason that males should be the 0 and females should be the 1 or the other way around. What we're probably more interested in is do either the sexes differ from the overall average, or the average for people in general. Okay? And there's a lot of situations in which that's going to be the more sensible comparison. And so the other sensible comparison you can code, and when I say sensible comparison, I mean the ones you're likely to encounter in most practice, there are alternatives. The default in S+, when I first started teaching this course, used to be a thing called Helmert coding. Helmert had come up with this wonderful system for situations that were highly unbalanced and highly non-orthogonal, and it was trying to sort of get the maximum contrast by a series of special coding to do it. I don't know how on earth it became the default in S+, because it's very hard to imagine a situation in which you really do need Helmert coding. Most routine, balanced experimental designs, you should be doing either treatment coding or the alternative I'm about to explain. So what is the alternative? The alternative is some contrasts or coding which use 0, 1, -1 indicator variables. So 1 equals 1 if in category 1, -1 if in the reference category, and 0 otherwise. I2 would equal 1 if you're in category 2, -1 in the reference category, and 0 otherwise. And again, you can't over-parameterize. If you go to IK -1, if you like, the kth category is going to be the reference category. It's going to equal -1 regardless. Okay? Again, we need to choose a reference category which equals -1 for all I1 up to IK -1. And we only need K -1 indicator variables again. If we try to fit all K, we're going to over-parameterize and lead to perfect multicollinearity. And why is it called sum contrast or coding? Because it's, the nice thing about it is the sum contrast, the sum constraint, is the sum of over all categories of nj affect j equals 0. Like these are the i's. So it's a suitably weighted sum. But if we've got a balanced design, nj is the same for all of the different categories, and so therefore we can, we can actually drop out the n quite happily. It comes out the front, okay, and then you divide it into the 0, it disappears. Oh, sorry. Somebody tell me if I've started writing off the bottom of the page. If balanced, weights are the same. The weights are equal. What do you think the constraint is in the first situation, in the treatment coding one? There's an implicit constraint there. So the constraint up here is that the dummy variable for the reference category is equal to 0. Okay? It's arbitrarily equal to 0, and that's the constraint we're setting. In other words, we're basically parameterizing under different constraints. And so I can't fit both of those two in the wrong spot without going back a bit. Okay, so we don't actually have to code those most of the time. If for some reason we weren't getting the R defaults didn't give us the things in the right order, didn't put our control group first in treatment categories, we could recode. All we've got to do is basically create these indicator variables in the background, C-bind them together, and they represent the variable. Okay? And notice they don't just have a single column, a single slope coefficient. You've got k columns in this. You've got k indicator variables. K minus 1, because one of them is constrained to being equal to 0 or to equal to negative 1, depending whether you're using sum or treatment coding. So you've actually got a k minus, you've got an n by k minus 1 matrix for your design matrix for that particular variable. So it takes 3 parameters, or a parameter for a slope coefficient for each of those dummy variables to actually code this up and implement it in R. So when we go back to the this is why it's taken 3 degrees of freedom to code up fertilizer, because there was 4 different categories. And here, if you like, are the coefficients for each of those, the dummy variables that have been created in the background. So the contrasts that are actually used, the default contrasts, were these. In other words, it's created, this is the coding for these variables. So the dummy variable for K2O plus nitrogen, K2O plus N, is 1 if we're in that group and 0 otherwise. The coding for this one is 1 in that group and 0 otherwise. Coding for this one is 1 in that group and 0 otherwise, and there is no dummy variable for the control group, because that's the constraint. That's the one that's been left out. And yes, I showed you how you can recover the group means from these. And notice I can actually basically tell R explicitly which contrasts I'd like to use, which approach I'd like to use. So if I want to sort of set fertilizer to contrast equals treatment, I can set it like that. And surprise, surprise, this gives me exactly the same model as I've seen before. These plots start looking very familiar. The analysis of variance table is invariant to the parameterization used. Okay, but that's exactly the same, even to the spelling of the terms involved. And that's exactly the same as well. The summary has got exactly the same things in it as well. Because really, all I've just told R to do is to go and use its own default anyway. So this is what R does for a 4-level contrast, treatment contrast. By default, it will not code the first one, that's the reference group. It will code up the second, third, and fourth levels. Okay, why was control the first level? Because it came first in alphabetical order. Okay, so there's a couple of ways you could trick R into doing things for you. If it didn't come first, you could put something like a AAA at the front of your, you could add AAA to the description for that particular fertilizer. So AA control, and that would, so it becomes the head of all the others. Alternatively, you could do your manual coding and create these dummy variables yourself. I think I do an example of that somewhere in the first few. So here we go. If we're not happy, here's creating the variables myself. So I'm actually creating dummy variables now. So they need to be the same length as the data. So it's not just a coding scheme, it's now basically creating the actual variables. But that's not the design matrix I can use, is it? Because it's got all 4 of them in there. If I tried to fit all 4 of them into something, what's going to happen? This is going to be over-parameterized. Whoa, no error message. But when you have a look at the summary, you find that what it's actually done, that actually is the intercept for the intercept is actually it's used the 4th group. It's deleted the fourth column of your design matrix arbitrarily. And it sort of said, because it's fitted first, second, and third, and it says, well, I can't fit the 4th as well. And so it's actually given me a slightly different parameterization, but it's still given me a sensible parameterization by removing one of the variables just arbitrarily. So if I wanted to force a thing on it, well, okay, that's really doing the same thing as I did before. I'm saying use variables 2, 3, and 4, C-band them into a design matrix and regress yield on that. And yes, looks very familiar. There is no plot 5 for some reason on this one. You have to go through the help files to find that one out. But really, it's exactly the same thing we fitted before. And yes, really all it is showing you is the differences between each of the groups and the control group. Somebody asked me the other day what the table apply function does. Well, it's actually not the easiest help. I said go read the help file, because that's always the way you can find out what a particular R command you haven't seen before does. However, I've probably sent on a bit of a wild goose chase because it's not a particularly easy help file to read. However, it's a very useful function to use. It's a good way of calculating sort of means, standard deviations, group variances, and it's one of these ones you need to play around with to see how it works. And again, I typically can't explain coding by standing in front of you and waving my hands. You need to have a go at it and try it and see. Okay? So go and have a look at the help file. Have a look at if you can't get anything else out of the help files, the useful thing you can get out of the help files is the examples down the bottom. Go and run those, and they typically will, you can just run those as they are because they will run on data sets that come with R, like the trees data did. So the table apply function is what I use to get the level means. Now here's the alternative, the sum parameterization. These plots are looking very familiar because they're exactly the same, because the plots and the analysis of variance table are essentially invariant to the choice of parameterization. All that changes is the values of the estimated parameters, because they're answering a slightly different question. So what question are these answering? Okay, 79 is now the intercept. Because this is a balanced design, that's actually the overall mean. So what the questions that you can use, you can answer with sum parameterization is, are there differences between these groups and the overall mean? However, if we just hide this for the moment and have a look, we can see that actually what we get is we get 3 parameters, because we've already got 3 dummy indicator variables, but we're missing one of the parameters. So really what's happened here is it's given us a difference between the control group and the overall mean, a difference between the second fertilizer, the first fertilizer treatment, the first active treatment, and the second active treatment, but we're missing that third active treatment and the overall mean. We don't have that fourth comparison. The standard error for it would pretty obviously be the same as the other comparisons. And we can actually work it out. We can work it out by inverting the sum constraint. Now remember that this plus this plus this plus the missing one have to add up to what under the sum constraint? 0. So 4 is the negative of minus 7 plus minus 13 is minus 20, plus 16 is minus 4. The negative of that is 4. Make sense? So all I've done is inverted the sum constraint, and I could basically draw another line here of 4.522, calculate another t-value, and I could work out a p-value for that t-statistic. Okay? So I could do the fourth constraint if I wanted to. But again, I'm starting to work the data to death, aren't I? The more comparisons of these I make, the bigger the chance that I'm going to actually come across one that's just correct, or seems to be significant by just sheer random chance. So here's the coefficients of Corn.lm3. And that's how I could add up those coefficients and so there's the coefficients. I could add those 3 together, take the negative of that sum, and that's the fourth one. That's inverting the sum constraint. Notice that's not the case if it was an unbalanced design. It's the weighted sum in an unbalanced design, and it becomes a lot more complicated. Another good reason for not unbalancing your design unless you absolutely have to by throwing things out. Here's the sum contrast for a 4-level variable. These are the defaults. So this is how you find out what R is going to do by default. Well, with a 4-level variable, it's not going to give you any indicator variable for the 4th level. It's going to give you one for the 1st, 2nd, and 3rd. And the first one's going to be 1 if you're at the 1st level, 0 otherwise, unless you're at the reference level, in which case it's going to be -1. Okay, so that's how the coding works. Just out of interest, that's what helmet contrasts look like. That's the coding for them. No, I'm not going to go into that at all, and it's not examinable. But have a look at the help files if you really want to have sort of... in fact, if you are dealing with highly unbalanced, non-orthogonal designs, you probably will find yourself going down that route. Helmut's trying to answer a particular problem there. I could also do the sum things manually. So again, I've just basically coded these things exactly the same way R coded them. That's the code I needed to do it with. And just quickly check that I get exactly the same model as I've been getting before. And yeah, everything else is staying the same as it was before. Though I've given you that code so that if you have to do your own manual coding, you've got some example code to follow. And I could basically force a different reference group using the same approach. What's the reference group this time? The control group. It's the first group. So up in the top 6, which are all the control observations, everything's equal to -1. And I've got indicator variables for the other 3. And this is getting quite tedious, but let's check those again. Yes, it really is the same model in a slightly different disguise. It still gives me the analysis of variance table, and it still gives me sensible parameters. Those slightly different parameters, notice the 4 is included now where it wasn't before. The one that's missing now is the control group. Is this model really appropriate? Let's calculate the variances in each of the groups. What's the maximum of those? What's the minimum? What's the ratio of the maximum to the minimum? 5.8. So the largest variance, group variance, is more than 5 times the smallest group variance, almost 6 times the smallest group variance. That's more than the number of groups I've got, which is 4. The answer is yes, we have a problem. Okay? But like I'd argued before, the problem is just going to be overinflating our things and reducing the likelihood that our inference is going to be significant. We're going to give us conservative inference. So I'd probably still go with this, because I think really the analysis I've got here would probably answer the researcher's question, which is the best yield. I've still got a good answer to that one. It's still the K2O plus nitrogen. So let's just use one of these models. Here's the Korn.lm2, which had, well, what coding did it have? It had treatment coding. And it was Okay. Now, what I've done in the rest of this is I've reproduced a bit of maths from the brick, because the brick then goes into testing a few different contrasts. Okay. What I want to do is show you a bit of key stuff now that is important in testing contrasts. So let's go and quickly get a copy of the brick up. So the bit I really want is at the bottom of page 5. There's actually a general recipe here for testing a contrast, any contrast you like, which is any linear combination of the means. So if I take a vector, h, which is basically just something I want to multiply by each of the means, so there's 4 numbers because it is 4 group means. I multiply by the group means. This just tells me that the variance for that is going to be sigma squared times the sum of hi squared on ni. Okay? What does that mean? Well, so I'll just write this down and then I'll sort of let you in on the secret. Okay, so I want to test a custom contrast, I can use this. So basically I can use it to get a standard error, because the standard error is the square root of the variance. Okay, so what's missing in this? What don't I know? Well, I typically don't know a sigma squared. I'm going to have to estimate it. The obvious estimate is the mean squared error. Okay, so I've got an estimate for that. If I've got a particular combination of the means I want to test, well, let's say I want to have a look at the mean for K2O plus nitrogen, which was the second group, minus the mean for the fourth group. See if the difference there is significant. Okay, because those were the two that were competing to sort of if they were going to be. So let's have a look here. So the question was here, this test tells me that this is significantly above the control group. This one is not necessarily significantly above the control group, but the sort of thing that remains unanswered is this the best group? Is it significantly above that group there? Okay. They differ by 12. Okay. You can pretty obviously see what the standard error is going to be. It's going to be the same because that's the standard error for the difference between two groups of size 6. But let's have a look at how we'd actually do it. So, for example, to test H naught, mu for K2O plus nitrogen, minus the mean for, what was the other one? Should have noted that down before I did. Fertilizer 4. N plus P2O, nitrogen plus potassium. Okay. Equals 0 versus the alternative. That mu K2O plus nitrogen minus this is not equal to 0. The standard error is found using H equals, well, I don't want the control group, so that's a 0 in this comparison. I do want the second group, that was the first fertilizer treatment. I don't want the third group because it wasn't included in the comparison either. And I want a -1 for the fourth group. Okay? So really, I'm comparing the mean for this group with the mean for the second group with the mean for the fourth group. So I'm putting a 1 in the second position and a -1 in the fourth position. So the variance of the sum of HI times YI is going to be S squared, estimate of sigma squared, outside of 0 squared on Ni plus, or well, N1 plus it's not good, not my day for not making silly mistakes. And that's probably quite familiar if you can remember two-sample t-testing. It's basically just the means of two independent samples, the standard error, assuming they've got the same variance. Okay? The sigma squareds come out the front. If we were giving them different, allowing them to have different variances, we'd have an S1 squared and an S2 squared and S4 squared in the top there. Okay? But this is the two-sample, this is the standard error for the two-sample t-test, assuming equal variances. And how do I finish off the test? Well, test statistic is T equals the observed difference minus 0 over the square root of, I can bring the S out the front, put the so it's just basically the observed difference minus the hypothesized difference over the standard error of the difference. The standard test statistic that we always have. The estimator minus its assumed value divided by the standard error of the estimator. And that will be distributed as a t-statistic with the error degrees of freedom. Why would I have the error degrees of freedom? Because that's the degrees of freedom associated with that S. Okay, so when you go back to the brick and have a look at what it does there, it's a little less perplexing. It's really just applying this formula. Okay, so here's the more general formula. And you know, this case, I could compare it against. There's a particular difference between these two groups. I could set C0 to be something other than 0. But really, that's all it is basically the observed difference minus the hypothesized difference over the standard error. And it does these sort of contrasts I can't remember. There's a bit where it actually does these sort of contrasts here. So here is testing a slightly more complicated contrast. That's basically testing a sum contrast. That's averaging the three active treatments and comparing it with the control treatment. Okay, that's a custom contrast. So the H involved here is just a little more complicated, but you can still use the same approach to get a standard error for that H. Okay, so if you notice we did look at the R's here. I need to go back in the. Here was the treatment coding standard errors. Guess what the standard error for the contrast we just did on the piece of paper is going to be? It's going to be 7.385 because it's the same as these standard errors. It's the comparison of two groups of size 6. The sum contrast standard errors are slightly different because they've got a slightly different H contrast vector involved. Okay? Okay, before we finish for today, though, I just wanted to sort of leave you with a couple of thoughts, and I'm going to finish off beginning of next week. We've now actually done quite a few contrasts with these data. Okay, so jelly beans cause acne, and they basically investigated and found no link. There was a p-value bigger than 0.05, which settles that. But then there was a secondary question. Only a certain colour causes acne. So they tested 1, 2, 3, 4, 5, 15, 20 different colours. And one of them here, yes, I don't really want you to, one of them here turns out to be significant. They've done 20 supposedly independent comparisons at the 0.05 level. Is their overall confidence really 0.05 on all of these? Nah. However, that doesn't stop some people going around publishing the news. Okay, so that's the issue of multiple comparisons. How do we get around it? Well, I don't think I have time to do that today. I'll just draw your attention to this particular quote, which is one of my favourites. If you talk to the data long enough, it will confess to anything. you should be aware of when you're making many, many tests in the same sort of situation, and you've found yourself in the Polynomial multi-comparisons. What we do about it? Well, you should remember a possible solution from first semester, from the regression model.